All right, the next study in our topic of thermochemistry, or the next topic in our study of thermochemistry, maybe that's the way we want to say it, is calorimetry. So calorimetry is the study of heat transfer. Metry comes from the Greek that just means to measure. So anytime you have a metry, you're measuring something. And calorie comes from I think originally comes from Latin. Calor is heat, and then the E was added by the French. So calorie is our heat. So to measure heat, and that's what we're going to look at. How do we measure heat transfer? So study of heat transfer between system and surroundings. Remember our fabulous, this is just a small version of our fabulous diagram from last week. System and surroundings. The end of last week, we talked about the fact that enthalpy is basically Q if we're at constant pressure. So we talked about transferring things into the system, out of the system. One thing to keep in mind that's super important is that heat and temperature are not the same thing. We tend to think about them exactly the same, and they're not. So heat is that quantity that's required to change something's temperature or required to be removed. So really, if you think about it, what's happening is if we increase our Q for the system, the response of the system is going to be an increase in temperature. So we're going to have that temperature change. You can have other things too. You can have a phase change depending on what temperature you're at. But oftentimes if we add heat to something, what we're going to see is that something is going to increase the kinetic energy of its particles. And if we increase the kinetic energy of its particles, we increase its temperature. So if we add that heat to the system, we're going to see a change in temperature as an increase of the system. In the same way, if we were to remove heat from the system adds heat to the surroundings, system loses that heat, we should see a decrease in the kinetic energy of the particles, a decrease in the temperature. And again, some other things can happen. We can have phase changes and things like that, but what we're going to look at today is how can we measure heat by measuring the change in temperature of the surroundings in order to relate that to the system. So heat absorbed by a system is directly proportional to the temperature change. So they're not the same thing, but they are proportional. So if we think about proportionality, maybe you've seen this before. This is just the symbol for proportional. Q, or heat, is proportional to change in temperature. And there's a constant of proportionality we can talk about, and that's going to be something called heat capacity, which is abbreviated with a capital C. Capital C is heat capacity, and that's going to be for any system, and it's going to be different for every system. It's going to be that constant of proportionality between heat and temperature, meaning how much heat do you have to add to change the temperature of the system. So by definition, heat capacity is the quantity of heat required to change a system's temperature by 1 degree Celsius. And so if we're going to change the temperature by 1 degree, how much heat do we have to add? Specific heat is the amount of heat required to raise 1 gram of a substance or system by 1 degree Celsius. So a little bit different, and we'll talk about units. Our units for heat capacity are usually going to be something like kilojoules per degree Celsius or joules per degree Celsius. Could be kilojoules per Kelvin, joules per Kelvin. I'll mention that when I come back. Specific heat is going to be typically units of joules per gram degree Celsius or joules per gram Kelvin. Could be calories per gram degree Celsius. Just like your heat capacity could be calories per degree Celsius. But all we're doing, the only difference in those units is plugging in the gram, because specific heat has to do with the specific system we're talking about. So then we can talk about how much energy does it take to raise a gram of it by a degree. So those are our two things here: heat capacity C, specific heat little s. One thing that's interesting is some books use C for specific heat, and so it's a capital C for heat capacity and a lowercase c for specific heat. It's nicer to use the S because a big C and a little c look really, really similar. So the S is kind of a nice thing there. All right, relationship between amount of a substance and energy transferred, our first equation here, and really our only equation today. There is one other one we'll look at, but it's more specific to heat capacity and a calorimeter itself when we're doing an experiment. The relationship between amount of substance and energy transferred. So you should recognize all of these symbols. Q, we have our heat symbol, and we've talked about that being typically in joules, could be in calories. Okay. Our S, we just looked at, is specific heat, and that is going to be, again, in joules per gram degree Celsius or joules per gram Kelvin specifically. And specific heat is specific for a given substance. So it takes more energy to raise the temperature of, say, one metal than it might take to raise the temperature of another metal, same amount of stuff. So it's specific. That's where that specific comes from. Mass is our M, and our mass in terms of this equation is going to be in grams, and our delta T is our change in temperature. Remember that a change in anything, always temperature at its final state minus temperature at its initial state. Temperature final minus temperature initial. Change in anything is always final minus initial. And so that's going to be our change in temp, typically in degrees Celsius. So there's our equation and what everything stands for. We'll start with a simple problem and then do one that's a little bit more complicated. Suppose you find a penny minted before 1982 in the snow. How much heat is absorbed by the penny as it warms from the temperature of the snow, which was -8 degrees Celsius, to the temperature of your hand, 37 degrees Celsius? Assume the penny is pure copper. So if we think about the things we know here, we want to know heat, which is our Q. We have a specific heat of copper. It's going to take 0.385 joules of energy to raise every gram of copper by a degree. According to the problem, we have a penny, which has a mass of 3.10 grams. And we have a change in temperature. That's going to be the temperature of our hand, because we're going to assume it'll be the temperature of our hand at the end, 37 degrees Celsius, minus its original temperature of the snow of -8 degrees Celsius. So we'll get a change in temperature of 45 degrees Celsius. And so we're going to plug in our values. Q equals SM delta T equals 0.385 joules per gram degree Celsius, 3.10 grams, 45 degrees Celsius. We get a value of 53.7075 on our calculator. Round that to significant digits, 53.7 joules. Let's make sure we understand where our units come from. Our grams cancel, our degrees Celsius cancel. We're left with units of joules, which is where we get our units of joules in our answer. And we can label that as 53.7 joules. So for that penny to go from -8 degrees to 45 degrees, takes into account the mass of the penny and the fact that the penny's copper. It's going to take 53.7 joules from your hand, from your body, to transferred to the penny to make that change. That's why your hand feels cold, because you're actually putting energy into the penny, and that's removing energy from your hand, and that's why you feel that sensation of this penny, it's cold. That's what's happening. So that's a pretty simple, straightforward equation to use. It's plugging in the right numbers that are going to get you where you need to be. Let's just head on to example 2 and see what that looks like. A block of copper of unknown mass has an initial temperature of 65.4 degrees Celsius. Sorry, I'm missing Celsius or degree symbols. The copper is immersed in a beaker containing 95.7 grams of water at 22.7 degrees Celsius. When the two substances reach thermal equilibrium, the final temperature is 24.2 degrees Celsius. What is the mass of the copper block? And specific heat for copper hasn't changed since the first example. And then the specific heat of water is given to you as well to 3 significant figures. So let's think about this problem. We have a cup of water. All right, how much water do we have? Well, we have 95.7 grams of water to be exact. And that 95.7 grams of water is at 22.7 degrees Celsius. We're going to take a piece of copper and drop it in there. All right, so our block of copper weighs something we don't know. That's what we're trying to find out. Our block of copper weighs some amount of grams, and that's our unknown. That's what we're trying to figure out. And our copper is at a temperature of 65.4 degrees Celsius. Okay, and then it says the two substances or the copper's immersed in the water and the two substances reach thermal equilibrium. That means their temperature together, temperature of the mixture, is going to be 24.2 degrees Celsius. Okay, now knowing all of that, what this is telling us is that is the temperature of both. So that's the final temperature of both. All right, in order to solve this problem, we can assume that the copper gave all of its energy, or not all of its energy, but transferred a bunch of heat to the water. That warmed up the water and it cooled down the copper until they were both at a temperature of 24.2. So what we need to think about is, what do we know? Well, we know the specific heat of water, the mass of water, and the change in temperature of water. We also know the specific heat of copper and the change in temperature of copper. What we don't know is the mass of the copper. So let's start with the water and figure that the heat gained by the water is going to be equal to the specific heat of water times the mass of water times the delta T of the water. And if we plug those values in, 4.18 joules per gram degree Celsius times our mass of the water, which is 95.7 grams, times our change in temperature of the water, 24.2 minus 22.7 gives us a change in temperature of the water of 1.5 degrees Celsius. So we have all those changes, and we're going to multiply those together, 4.18 times 95.7 times 1.5, and that's going to give us the amount of energy the water gained from the copper. That's going to be 600.039 joules. Obviously, not all of those values are significant. Going back to the 1.5 degrees Celsius, I'm going to go ahead and put a line over my first zero to say this has two significant figures in it right now. And I'm going to carry that forward, but I'm going to use all my digits when I plug in my numbers. Now, if the water gained that much energy, we can also assume that the copper lost that much energy. So our heat of the copper is going to be equal to our specific heat of copper times our mass of copper times our delta T of copper. In this case, because the water gained 600 joules from the copper, we can assume that the copper lost 600 joules of energy. We know the specific heat of the copper. We don't know the mass, that's what we're looking for. And our delta T in this case is going to be negative 41.2. I'm going to move this over. Negative 41.2 degrees Celsius, because our final temperature was 24.2. We subtract our initial temperature of 65.4, we get negative 41.2 degrees Celsius. If we use those values and solve for M, you're going to get an M value equal to 37.8 grams, which, again, if we go back to significant digits, this one had 2, this one has 3, this one has 3, 2 in our answer. We can assume that the mass of the copper is 38 grams. So that copper block would have had to weigh 38 grams in order to change the temperature of the water by that much. Now, obviously, we make some assumptions there. We didn't lose any energy anywhere else. And all of the heat lost by the copper was gained by the water. And then we can solve a problem like that. I'm going to stop the video here and do the calorimetry on a separate video. Thanks.